Okay, welcome back to linear algebra. We're going to do the second of 2 days of section 1.6, talking about another very important topic for the rest of our course, dimension. Last time we talked about bases. This time I want to talk about something called dimension. So you can see the goals of the lecture. They're written there. I want to state and prove an important theorem, the replacement theorem. It's theorem 110 in our book. And really, that theorem is a means to an end. I'm really the most interested in these two corollaries to it. All right, so we'll state those things as we go. And then along the way, we'll make this definition, the title of the lecture, this very important notion, the dimension of a vector space. Okay, so those are our objectives, our goals. Let's just get going. Here I've got a statement of the replacement theorem. It's all written out so we can go a little bit faster here. I'll probably just denote it or refer to it rather by these initials, at least in this lecture, RT. Okay, so what's the replacement theorem say? If we're given a vector space over a field F, and then we take some generating set of it, G is some generating set, and we're going to specify it's a finite generating set with n elements. Okay, any spanning set with n elements is part of the hypothesis. Okay, and then you take some other set here. We'll, as we're speaking, we'll kind of highlight these things. So I've got the generating set. It's got n elements in it. And then another part of the statement of the theorem is you take some other set, L, totally independent of G. It's a linearly independent set with m elements. Okay, so those are sort of the setups. The L and G don't have anything to do with each other. G generates, it's got n elements, L is independent, it's got m elements. So the statement of the theorem is that then m is no more than n. A linearly independent set never has more elements in it than a generating set. And moreover, and this is why it's called the replacement theorem, there's some subset of G that's got the difference, n minus m elements, and if you replace the complement of that subset with L, you'll still have a spanning set. Okay, so that's the replacement theorem. Here I've drawn, this isn't the most exciting picture you're ever going to see in your life, but this is kind of how I visualize this theorem. So I'm given this set G, I'm visualizing it in this picture like it's this line, yeah, and the length of it is kind of the number of its elements. It has n elements of it, it spans G. And then we're also given this set L, it has m elements in it, it's linearly independent. So the theorem is saying that there's some piece of G called H, and it has n minus m, the difference elements. And if you take H and put it together with L, you'll still have a spanning set. So the way I like to think about it is you're replacing the part of G that's not in H with L, keeping a spanning set. It's called the replacement theorem. Okay, let's take a look at the proof. It's going to be kind of a nice application of the principle of mathematical induction. Some of this stuff I wrote out ahead of time to keep this going a little bit faster, but after this page, we'll write together. So I'm going to induct on the number of elements in the set L. I'm going to induct on M. Okay, so I'm going to assume that my spanning set has at least one element in it, because otherwise the theorem is kind of trivial. If your spanning set has no elements in it, then your vector space is just the zero vector space, and there's not really much to say. Okay, if n is zero, that m has to be zero. And there isn't much to say. So let's fix this n. It's at least one. And now I'm kind of thinking about the base case. If m is zero, my independent set has no elements in it, well, then L must be the empty set. And I can just take H to be G, and the theorem is satisfied. I don't like to do a lot of scrolling when you're watching these because it makes you sort of dizzy. But all I'm saying is that if the set L is empty, it's not here at all, well, then just take H to be all of G. And the theorem works, right? Because when you union the empty set with something, you don't change it. So that's kind of just a trivial case. Okay, now I'm going to set up my induction here. So I'm going to let S be the set of those natural numbers that are at least zero. And it's a complicated induction hypothesis. It says that whenever you have a spanning set G with n elements, okay? And whenever you have a linearly independent set L that has m elements, then I'm going to assume that S is the set of all those m's for which the conclusions would have to hold, that m under that circumstance would be no more than n, and you can do this replacement business. Okay, there's a subset of G such that the complement G minus H has n minus m elements, and the span of L union H is still V. So S is the set of natural numbers for which that's true. And what we did up here in our base case is we showed that 0 is in S. Okay, so S has an element in it. That's our base case. 0's in there. So now the induction hypothesis. Suppose for some m that's at least 0 that it belongs to this set S. And to use the principle of induction, our job is to show that the element m plus 1 is in the set S. Okay, so what does that mean? That means I have to take a linearly independent subset with m plus 1 elements in it. So let's give some notation for that. Okay, let's call the elements of that subset V's. So let's let L be a set of vectors, V1, V2, up to, say, Vm plus 1. And it's a linearly independent set. Okay? Good. What do we have to do? We have to show a couple of things. We have to show that m plus 1 is no more than n, and that we can find this subset of G that has n minus the quantity m plus 1 elements in it, that when we union it with our L, we still span V. Okay, so that's our goal. If we can show this L does that, then we can conclude that m plus 1 belongs to the set S, and the principle of induction will tell us every number belongs to the set S, which is what we're trying to do. All right, good. So L is a linearly independent set. Well, let's let L prime, just for some notation, L prime is the first m elements. So stop at Vm. Okay, so it's a subset of L, and it's also independent. I don't have the theorem number right in front of me here, but we have a theorem that says that subsets of linearly independent sets are linearly independent. So this L prime is also an independent set, okay? So by the induction hypothesis, because L prime has m elements, so by induction, what do we know? We know that, well, first of all, m is less than or equal to n, because the set m, the number m rather, belongs to the set S. So we know that m is less than or equal to n, and there's some subset, I'm going to call it H prime. So H prime, I'm going to name its elements. I'm going to call them, say, U's. U1, U2, up to Un minus m, because that's how big this H prime is. It's a subset of G, yeah? And I know that this L prime union H prime spans V. So the span of L prime union H prime is still the whole vector space V. That's because M belongs to S. That's by our induction hypothesis. Okay, M belongs to S, so these two things are true. M is less than or equal to N, and there's a subset of size N minus M whose union with L prime is the span of it rather, is still V. Okay. Well, we know one element of V is this Vm plus 1. So there must be scalars. I'm going to call them A's and B's. How many A's are there? The number of elements in L prime. There's m of them. So there's some A's and then also some B's, B1, B2, up to Bn minus m. They're scalars. And what do those scalars do? Well, Vm plus 1 is a linear combination. So if I take A1, V1, and so on up to AM, VM, plus B1, U1, and so on up to Bn minus M, Un minus M, I know that that equals Vm plus 1, and that's because of this spanning statement. Yeah, every vector is a linear combination of vectors in L prime, that's the V's, and vectors in H prime, that's the U's. Okay. Okay. So if n and m are equal, let's think about that case. So if n is equal to m, right? Well, then n minus m is 0. And n minus m is the number of elements in H prime, so that would mean that H prime is the empty set. Okay, so that means that there really aren't any elements in this sum with the B coefficients. So that would put Vm plus 1 in the span of L prime. Right? But that means that the set L isn't linearly independent. Right? Because Vm plus 1 belongs to L. So if it's in the span of L prime, then the set L wouldn't be linearly independent because I'm writing one of its vectors, namely Vm plus 1, as a linear combination of other vectors, namely the things that are in L prime. So that's a contradiction. So n can't be m. We've already established that n is at least m, so it follows that n has to actually be strictly bigger than m. And in particular, since these things are integers, n would have to be at least m plus 1. All right, that's one of the things that I wanted to be true. In order for m plus 1 to be an S, sorry about the scrolling, but I have to do it. In order for this thing to be an S, one of the conditions is that m plus 1 had to be less than or equal to n. Well, we've got it. And m plus 1 is less than or equal to n. So what I need to do now is produce this set that's the right size that I can replace part of this set G with to keep a spanning set. Okay, so for the same reason that we just said, not all elements BI can be 0. When you're looking at this sum up here, if all of the B's were 0, well then again, Vm plus 1 would be in the span of L prime. It's a contradiction. So at least one of these B's isn't 0. Without loss of generality, I'm going to say it's B1. All right, without loss of generality, I'm going to assume that B1 is not 0. So what am I going to do? I'm going to take this sum, this equality, sorry, that I'm underlining. I'm going to solve it for U1. That's all I'm going to do. I'm going to write some algebra, but I can solve it for U1 because the coefficient of U1 isn't 0. All right, so let's see if we can't do it. I have to try to leave it visible there. So what is U1 going to equal? Well, U1 is going to equal 1 over B1 times, what would we have? We'd have the Vm plus 1. We'd have all of the A terms, but their coefficients are going to all be negative because we're going to subtract them all. I'm just going to write AJ V sub j. And then we'd have all of the other B terms. So that one, I'm going to write sum B sub k, U sub k, and let me be explicit here that k would go from 2 up to n minus m. Here, this j goes from 1 up to m. Okay, so that's just solving that thing for U1. Okay, so let's let H be H prime except for this U1 vector. All right, so how many elements does H have? Well, it has n minus m minus 1, or that's n take away the quantity m plus 1. It's got the kind of right number of elements for our induction height that we're trying to meet to show that this thing is in the set. Okay, so we'll let you, and then what are we going to notice from this equality? The fact that u can be written as in that form. What do we know about that u1? u1 belongs to the span of L union H, right? Because look, what is L? L is all the V's. So Vm plus 1 and each one of these Vj's, those are in L. And then what's in H? Well, H is exactly the U's that don't include U1. So U1 is in the span of that set L union H. Okay? U1 is in the span of L union H. But if we drop off the Vm plus 1, if we just look at L prime union H prime is certainly a subset of L union H. Sorry, that's not true. That's not true because of U1. But L prime union H prime is certainly in a subset of the span. That's what I meant. The span of L union H. That's because the one and only vector that's missing here, U1, happens to belong to that span. All right? So L prime union H prime belongs to the span of L union H, but L prime union H prime spans V. The span of L prime union H prime is equal to V. So that means that the span of L union H is equal to V, right? Because the span of L union H certainly can't be any bigger than V, and it contains this set that spans our vector space. So L union H spans V. So we've done it. We found this set H. It has the right number of elements. It has n minus m plus 1 elements. And L union it, I'm just going to write it again, the span of L union H is equal to V. So this shows that m plus 1, the next number, satisfies the conditions to be in our set S. So our set S is equal to the set of all natural numbers by the principle of mathematical induction, and that precisely proves our theorem. All right, good. So that was kind of a complicated induction argument. Let's look at these two aforementioned important corollaries. Okay, so that replacement theorem is really a means to get at these two corollaries. Here's the first one. The first one says that if you have a vector space with a finite basis, then any two bases have the same number of elements. So if your vector space has a finite basis and you find a basis with 13 elements in it, every basis has 13 elements in it. So how does this follow from our theorem? Let's suppose that we have two, beta 1 and beta 2 be bases with, say, n and m elements. Actually, let me switch my notation scheme. I think it'll be better with n1 and n2 elements, respectively. Right? So you know what I mean by that, i.e. beta 1 has n1 elements, beta 2 has n2 elements. Okay? And now beta 1 is a linearly independent set. And the span of beta 2 is V. So by the theorem, by the replacement theorem, we know that N1 is less than or equal to N2. Any independent set has no more elements than any spanning set. But we can reverse the roles, right? Beta 2 is a basis. It's also linearly independent. Beta 1 is a basis, so it also spans. So using the replacement theorem again, you get that N2 can't be any more than N1. Well, two numbers that satisfy both of those inequalities are equal to each other. Cool. This is an important fact, that any two bases in a vector space that has a finite basis have the same number of elements. Very important fact. In fact, we're going to give a name. So we're going to call a vector space finite dimensional if it has a finite basis. Okay, makes sense. Finite dimensional, it has a finite basis. And the number of elements in what we just proved, it doesn't matter which basis, the number of elements in any basis is called the dimension of the vector space. Okay, because the number of elements in any two bases is the same. That number depends only on the vector space, not on the basis. So we're going to call it the dimension of V. For shorthand, I'll write it like this, dim V. Sometimes you'll see me put parentheses around the V. I don't mean anything else. This won't come up with us too much, but occasionally, you know, the field involved will have some influence on what this dimension is. So if you're trying to emphasize what the field is, that's the place that people write it. So the field gets written down here as kind of a subscript, the dimension of V over F. Yeah. So if it's understood what the field is, then you can use these more brief notations. Okay. If a vector space isn't finite dimensional, then we call it infinite dimensional. So an infinite dimensional vector space, by definition, is a vector space that does not have a finite basis of any size. Okay, so it's an infinite dimensional vector space if it's not finite dimensional. Let's look at some examples. Do you remember our example? If V is the zero vector space, it has a basis that's the empty set. So the dimension of it, the dimension of the zero basis vector space is 0. The vector space that contains the 0 vector alone is 0 dimensional. What about Fn? Fn, we said that the standard basis consisted of these n vectors e1 to en, the n standard basis vectors. So the dimension over f of the vector space of n tuples is n. It's an n-dimensional vector space. So the number of coordinates, the length of the tuple is its dimension. What about polynomials of degree less than or equal to n? Do you remember what its basis was? I mean, I shouldn't say because it has many, but do you remember what a basis is? It's the basis of polynomials, or monomials rather, that start with x to the 0 and go up to x to the n. So the dimension of the polynomials of degree less than or equal to n is, be careful, it's n plus 1, right? Because if you're counting these things by the exponents, you need to remember that there's this 1, this x to the 0. So polynomials of degree less than or equal to n has dimension n plus 1. What about polynomials themselves? No cap on the, yeah? So remember the basis for the vector space of all polynomials, well, that basis was infinite. And no finite basis could, no finite subset of polynomials could be a basis. If you took any finite subset of polynomials, there would have to be one in there or more than one in there, but there has to be a maximum degree. And linear combinations of those things would never have a degree bigger than that. They couldn't possibly span. So this is infinite. PF is an infinite dimensional vector space. can't have a finite basis. What's the dimension of our m by n matrices with entries in F? You remember that basis beta? I'm going to be just a little brief here and say it was the set of all EIJs, the elementary matrices. And maybe you remember that I, the row subscript, well, it can be any number between 1 and n, and j could be any number between 1 and n. So how many such pairs ij are there? There's m times n of them. So the m by n matrices is an m times n dimensional vector space. In particular, the dimension of the square matrices is n squared. Nice. Cool. In this course, we'll primarily focus on finite dimensional vector spaces. We won't play around with much with infinite dimensional vector spaces. They tend to be a little bit different of a creature. They have a lot in common. A lot of the linear algebra theory is the same for finite and infinite dimensional vector spaces, but some of it isn't. And in this course, we'll tend to focus on the finite dimensional case. Okay, got one more corollary. It actually has 3 parts. It has 3 parts. I think I'm going to be a little bit brief about just sketch the proofs of these things. I won't try to write out too much. This video is already getting a little bit long, but let's at least say what it says or see what it says. So we're given a vector space with dimension n. Very important. We're given a finite dimensional vector space. Okay, so this is a theorem about finite dimensional vector spaces. And then what does it say? It says if you take any generating set for it, well, that generating set has at least the dimension number of vectors, okay? And moreover, if it has exactly that number, then it's a basis. So if you're a generating set, you minimally have the number of elements that's equal to the dimension. If that happens to exactly be the dimension, then you're linearly independent, you're a basis. Yeah. The second condition or theorem of statement of the theorem is that if you have a linearly independent subset with exactly n elements, n being the dimension, then it spans. Yeah. So remember, to check something is a basis, you have to check 2 things: span and linearly independent. Well, this theorem is saying if you happen to know the dimension of the space, you can check just one of those. If you have a spanning set that's got the dimension of v elements, it's independent. If you have an independent set that has the dimension of v elements, it spans. So it's sort of a time saver theorem. The third condition is that every linearly independent subset can be extended to a basis. So what do I mean by that? What do I mean by being extended? What's it mean to be extended to a basis? It means if you give me a linearly independent subset, I can find some other subset that I can union with your linearly independent set to become a basis. I can add things, if you like, to L until I get a basis. Okay, so how to sketch the proofs of some of these things. Let me try to leave. I'm going to be just kind of brief here and write just sort of chalkboard style. So we have a generating set with at least n. Remember n, let me write it here just to emphasize, it's the dimension of v. Everywhere in this proof, n is the dimension of v, right? So why would A be true? If you have some generating set, well, then the replacement theorem says that there's some subset of it that's a basis, right? Or not the replacement theorem, sorry, the theorem 1.9, that if G generates, let's write it. So if G generates V, then theorem 1.9, sorry, I'm being a little spazzy here. If G generates V, then there exists some subset, H of G, that's a basis. That's theorem 1.9, not the replacement theorem. It's theorem 1.9 from the previous lecture, right? So H has n elements in it. Any two bases have n elements in it, right? But H is a subset of G, so G has to have at least n elements. It can't have fewer, right? Any subset or any superset has to have at least as many. And then moreover, if G equals n, then H is equal to G. H is a basis, so is G. So that's the proof of part B, or part A, excuse me. How do we prove part B? Let's remind ourselves what it is. You have a linearly independent subset with dimension of V elements. We have to show it's a basis. We have to show it spans, right? Well, let's use the replacement theorem. If L has n elements and L is linearly independent, well, since any basis has n elements in it, by the replacement theorem, if beta is any basis, and in particular, that would mean the span of beta is V, then there exists some subset of beta with n minus n or 0 elements, and L union that subset still spans. The replacement theorem says that. But if H has 0 elements, it's empty. So L generates. So L must be a basis. It's a linearly independent subset that spans. Finally, what's the third one say? The third one is that every linearly independent subset can be extended to a basis. Okay, well, let's use the replacement theorem again. If you have this linearly independent subset, let's say it has m elements in it, it's linearly independent. So taking our cue from the previous part, there has to be a subset of some basis and that subset has n, the dimension of V minus m elements, and L union that subset still generates V, right? But we just proved in part A that a spanning set has at least n elements in it. So this set, L union H, has at least n elements in it by part A. L has m elements in it. H has n minus m. I don't know if they have any overlap, but certainly even if they did, it would be the case that their union would have no more than m plus n minus m, or n elements in it. So again, if those two inequalities are both true, that union, L union H, must equal n in size. But if you have a spanning set with n elements in it, then again by part A, so L union H is a basis. All right, so that's what we were trying to show. We extended L to a basis. Okay, well, so I'm going to stop it there. Thanks for listening.